everyone. So in this class, I'm going to discuss the operation of diode clamper circuit. So clamper circuit is basically used to shift the reference level or the DC level of any waveform. So in previous class, we already discussed about the clipper circuit, where some portion of any particular waveform is removed by using clipper circuit. But note that in clamper circuit, there will be no change in the signal waveform. Let you are applying a sinusoidal signal, so output will be sinusoidal. And if the input is a pulse, so the output will be pulse. So there will be no change in the shape of the waveform, and the input and output voltage magnitude, that is peak to peak value if you calculate, so that is also same. Okay. So let us see how we can design clamper circuit. Now in clamper circuit design, the one common component will be there, that is a capacitor. Okay. So the capacitor will store some temporary charge. Okay. And that charge will be used to modify or to shift the DC voltage. Okay. So the capacitor is mandatory while designing the clamper circuit. The circuit is like this. Here we are applying V in, and here we are getting output V. And just to simplify our analysis, we assume that the diode is an ideal diode. So that is, when the diode is on, it will be replaced by the short circuit, and when the diode is off, that is reverse biased. So the diode will be replaced by open circuit. And at the beginning, we assume that there is no previously stored charge inside capacitor. That means the voltage across capacitor, VC, is 0. If Q equal to 0, so of course the voltage across capacitor will be 0. So at time t equal to 0, so we can say the capacitor is shorted. It behaves like short circuit. So let we are applying a square wave. Okay. So let amplitude plus P and minus P. Okay. So during positive cycle, this one will be plus and this one will be minus. And see, initially the capacitor will be shorted because the charge is 0, as I told you. And the diode will be forward biased because see, the P side of a diode is connected to some positive potential with respect to N side. So diode will be forward biased and some current will flow through the diode and capacitor. Okay, because the circuit is completed and some current will flow. And when the current is flowing through the capacitor will charge, and the capacitor will charge up to the peak value, that is plus V. Okay. So here during positive cycle, see, the diode will be shorted and the capacitor will charge up to peak value of V. So we can mention that the voltage across capacitor, so that is equal to VC, so that is equal to plus V. And since the diode is on, that means we can replace the diode by short circuit, assuming it is the ideal one. And if you consider it is a practical diode, then it will be replaced by a 0.7 volt voltage source if the diode is silicon diode. Anyway, so here just to simplify our analysis, we assume the diode is ideal. So diode behaves like short circuit. Okay. So of course the output V0 will be 0. Okay. So here the output we are getting V0 will be 0. So this is the situation for positive cycle. So for positive cycle, that means for 0 to T by 2, positive half cycle. Okay, so the output we are getting 0 and the voltage across capacitor we are getting, that is equal to plus V. Similarly for negative cycle, that means from T by 2 to T. So we are talking about this part, negative cycle. Okay. So let's place the diode. Yes. Now see, for negative cycle, the diode will be reverse biased because see the negative cycle, this terminal will be minus and this one will be plus. So the N side of a diode, okay, is connected to some positive potential, okay, and P side of a diode is connected to what? Some negative potential, okay. So the diode will be off. So if the diode is off, so you can consider the diode is open, and at this condition, the output voltage V0 we can calculate by applying KVL in the circuit. Okay. So if we apply KVL in the circuit C, the equation will be like this: V in will be equal to the voltage across capacitor, so that is equal to VC plus output voltage V0. So V0 will be V in minus of VC. So the V in we are applying, that is equal to minus V because we are in the negative cycle. So V in equal to minus V, and VC, that is the voltage across capacitor. Okay, it is already there in the positive cycle. We already decided that part. It is minus V. So the output we are getting V0 equal to minus 2V. See, in the positive cycle we are getting output 0. In the negative cycle we are getting V0 equal to minus 2V. So let's plot the graph. So if we plot the graph of input and output, so time axis, let this one is your input, and so this is plus P, this is minus P, this is 0, T by 2 and T. Okay. Now if we plot the output here, so V0, okay, is 0. See, for positive cycle, as per our analysis, we are getting 0, V0 equal to 0. So for positive cycle, 0 to T by 2, the output is 0 here. Okay, so let's mark it. So up to this part, output will be 0. And for second part, we are getting output equal to minus 2p. So here we are getting output equal to minus 2p, approximately like this. Okay. So this one is a 0. So this one is minus 2p. So the reference level we can say is a midpoint. So it will be minus p. Okay. Now see the input and output. So this is the input waveform and this one is the output waveform. See, at the output we are getting same square wave. Even if we calculate the peak-to-peak voltage, it is twice P. It is also twice P. Okay. But see the DC level changes. So previously, the DC level was centered at 0 for the input. Now the DC level shifted in the negative side, that is minus 2, minus P. Okay. So this clamper, we can say it is a negative clamper. Okay. So this one is a negative clamper. Now one question may arise in your mind that why we need to shift the DC level. So actually when we are designing some circuit, especially in amplifier, you know the amplifier needs biasing. So when you are applying some signal, so we need to adjust the DC component. Okay. So sometimes we need to shift the DC level, okay, up to some required value so that the next block where we are applying the signal, it will work properly. Okay. For those purposes, we need to shift the DC level of any signal. So we can do this by applying this, by using this clamper circuit. So this is the example one. So let's solve another one. So in the next example, let the polarity of a diode is just changed. That means now the diode is connected in this way. So what will be the output? And later we are applying the same type of pulse. Now, just to simplify the analysis, do one thing. Always start your analysis from that cycle where the diode will be on and the capacitor will be charged. Because see, in this circuit, the capacitor will charge only when the diode is on. And see the circuit, the diode will be on in negative cycle. So always start your analysis from negative cycle. Okay, because the operation of clamper circuit, the output voltage depends upon the voltage across capacitor. The amount of shifting in DC level or DC voltage you are getting, so that is due to the capacitor. So your first job is to charge the capacitor, and so you have to start the analysis from that cycle where the capacitor will be charged, that is the negative cycle in this case. Okay. And since it is a periodic waveform, so the cycles will be repeated. No? So if you start your analysis from negative cycle, okay, so then you can do it for the next positive cycle. What will happen? The same value will be here. Yes, for time t equal to 0, the waveform will be a little bit different. Okay, but after that, okay, so the same repetitive waveform will be there in the output. So let's start in the negative cycle. So this one will be minus and this one will be plus. And as per our previous assumption Q0, so voltage across capacitor will be 0. So the capacitor will be shorted and the current will flow. So current will flow in this direction. Okay. So diode is on, the current will flow. And when the diode is on, okay, so we are talking about negative cycle. So the diode is on. So the first thing we can write V0 0, assuming the diode is ideal. Okay. So assuming ideal diode. Okay, so output is 0. So now see the voltage across capacitor VC. So what will be the value of capacitor voltage? So capacitor will charge up to the negative voltage, means now the voltage we are applying minus V. So VC will be equal to minus V. Okay, even you can check it. If you place 1 meter here, so this point is minus, this point is plus, and the voltage across capacitor, that is same as minus V, that is V in. Okay. Now in positive cycle, so in positive cycle, the things will be opposite. That means, and the voltage you are applying, this will be plus and this will be minus. Now the diode will be off. So reverse bias. So the diode is off. Okay, so you write diode off and hence open. It is open circuit. Okay. Now again you follow the same strategy, apply KVL. What result we are getting? So this the input is V in. So V in equal to voltage across capacitor plus V0, or simply V0 equal to V in minus VC. Now in this case, in the positive cycle, or V in equal to plus V, and VC value we already derived that is minus V. So minus of minus V, that is plus V, that is twice V. So the output we are getting twice V. So for negative cycle output 0, for positive cycle output will be twice V. So let's plot the graph. So time axis, this is V in plus V minus V. So the output we are getting V out. Okay. So for negative cycle, so this cycle output will be 0. For this part, output will be 0. Okay. And for positive cycle, see, if you consider it is from 0, so here the output you will get that is different. Okay, because we start our analysis from here. So for positive cycle, that means the things when this one will be repeated, the output you will get plus 2V. Okay, so you can put a copy here actually. So if you take a part of the waveform that is not starting from time t equal to 0, because a time t equal to 0 situation will be different. It shifts the reference level in the positive side, so it is a positive clamper. Because see now the 0 level is here, and the reference level, if we mention, so that is plus V, and this one is plus 2V. So it is an example of positive clamper. Now similarly, you can apply the sinusoidal waveform at the input of any clamper circuit. Let's discuss one circuit. Okay. Let we have a circuit like this. Now instead of applying a square wave, I am applying a sinusoidal waveform at the input. Then what will happen? Now see, when the diode is on, that is here for positive cycle, when the diode is on, this capacitor will charge up to the peak value, so that is Vm. Okay, So for positive cycle, so we can write when diode is on, capacitor will charge up to peak value of sinusoidal waveform, that is Vm, this one, V peak or Vm. Okay. Voltage across capacitor plus output voltage, or simply V0 will be V in minus of Vc. So that is V in minus of Vm, because the voltage across capacitor is nothing but Vm. So basically output voltage, that is basically the difference between input voltage and the capacitor voltage. So how we can plot the graph? So let us see. Let the input voltage we are applying. So it's a sinusoidal waveform like this. 0, pi, 2 pi. This is the V in. What will be the output voltage? Okay. So T. This is input. Okay. So our formula V0 equal to V in minus of Vm, where Vm is the peak value, this one, Vm. Okay. So when V in 0, see, because at time t equal to 0 here, the V in equal to 0. When V in 0, so V0 equal to minus Vm as per this formula. Okay. And when V in equal to Vm here, V0 equal to 0, because see this equation, and when V in equal to minus Vm here, so V0 will be minus 2 Vm. So the output we are getting, if we plot the output here, so let's plot the graph of output. Okay. See, when V in 0, V0 equal to minus Vm. So let here, V0 equal to minus Vm. This is 0 axis. When V in equal to Vm, V0 0. That means here at this point. Okay. So when V in equal to Vm, V0 equal to 0. So it will touch like this. And again, when V equal to 0, V0 equal to minus Vm, V0 equal to minus Vm. And when V equal to minus Vm, V0 equal to minus 2 Vm. That means at this point, output will be what? Output will be minus 2 Vm. Okay, so this is minus 2 Vm. Now see that thing, the entire waveform shifted what in the downward direction, the negative side. See the reference level. The reference level is now the minus Vm. Previously it was 0. So it is also one type of negative clamper. And the waveform we are taking, it is different. It is a sinusoidal waveform. This is another one example. Now, finally, we shall discuss the last one, that is biased clamper. Now, see, in all previous example, there was no additional bias voltages. Okay, so in Clipper circuit, we can use some additional bias voltage which is connected in the series with the diode, so to get the required amount of shifting. Okay. But see here, no such additional bias voltages are connected in those circuits. So those are unbiased clamper. So where the output you are getting, the shifting is one complete cycle. See here, the amount of shifting, okay, is equals to this. Okay, so previously the DC level was at 0, now it's shifted to minus. So the amount of shifting is V. Okay, similarly in this circuit, previously DC level was 0, now it is plus V. The amount of shifting is V. So one peak. The same thing is true for sinusoidal signal. But if I want to shift it as per my choice, so that it will shift by an amount of 1 volt, 2 volt, etc., then you need to add some extra DC voltage along with your the input signal, whatever the circuit configuration you have, you need to add one extra DC voltage. So let us see how we can do that. Let the circuit is same as before. Now here we are adding one extra DC voltage. Let this name is PV. It's a diode, capacitor, same as before, and we are applying the same type of waveform, that is a pulse plus P minus P. Okay. And again, the analysis, the charge, the positive cycle at the beginning, the charge stored inside capacitor 0, so voltage across capacitor will be 0 at t equal to 0. And one thing you need to follow, the voltage you are applying, the V in, it should be, okay, this during the positive cycle, the plus V, so V in equal to plus V, whatever, it should be greater than VB. Okay, otherwise the diode will not be on. Okay. Suppose here you are applying a voltage of 5 volt and VV is 10 volts, so of course the diode will not be on. So this peak voltage, it should be greater than VB. Okay, let's remember that part. Now in positive cycle, the diode will be on because see that you are applying a 20 volt here. Capacitor behaves like short circuit initially, and here the voltage is VV, so diode will behave like short circuit. Okay, so then in that condition, the equivalent circuit will be like this: voltage across capacitor 0. Okay, so once the capacitor is fully charged, the voltage across capacitor, okay, will be VC. That is the let's see how to calculate this. Okay. So this is the equivalent circuit where the diode is shorted and this voltage is VV. So this is V in, this is V naught. So one thing is clear that V naught will be equal to VB during positive cycle. Okay. So this voltage will appear at the output. So V naught, the voltage between this to this is nothing but VB. Okay. Now see, now we want to calculate the voltage across capacitor because that is important. Next cycle, we need this VC value. Okay. So the voltage across capacitor we can calculate by using KVL. So V in will be equal to VC. Okay. The voltage here VC plus, see the voltage V naught, now it is VB. Okay. So VC is nothing but V in minus VB. Okay. For example, we are applying this is plus 20 volt and this one is minus 20 volt and the voltage we are applying a 5 volt. So it will be simply 20 minus 5, that is 15 volt. So the voltage across capacitor, it will be 15 volt. Okay. And simply you can check the circuit. Here it is 20 volt, here it is 5 volt. Okay. So the potential difference between two ends, it will be simply 15 volt. Okay. So this is all about this circuit at positive cycle. Now in negative cycle check, the negative cycle, the diode will be off and you simply open the diode. Okay, diode is off, open the diode and output voltage V naught, it's right here. So in negative cycle, diode off, so the output voltage V naught, it will follow the same principle, V naught equal to V in minus voltage across capacitor. So now our V in is minus 20 and the voltage across capacitor we already calculate, that is equal to 15 volt. Minus 15, that is minus 35 volt. Okay. See the output we are getting. Positive cycle V naught equal to VV, that is plus 5 volt. Negative cycle, the output we are getting minus 35. So let's plot the graph. The input we are applying like this, plus 20, minus 20. So this one is V in. So the output we are getting, okay. So for positive side 0 to t by 2, the output we are getting plus 5. So this one is plus 5. And here we are getting minus 35. Minus 35. So this is the output. And this one is input. See the difference. The peak to peak voltage remains same, 40 volt. Here also it is same, 40 volt. But see the shifting, the signal shifted in the downward direction, but the amount of shifting is decided by what? The voltage VB. Okay. So this type of circuit is called biased clamper. Biased clamper. So similarly, you can change the polarity of this voltage, or you can change the direction of the diode. So depending upon that, you will get a different types of waveform. Maybe it is a negative clamper, maybe it is a positive clamper. Okay. So this is the basic working mechanism of unbiased and biased clamper circuit using diode.